Okay. Moment, yes, stopped. Okay, and participants. Yes. Okay, so we start our seminar. Our speaker today is Stephane Zaleski. Just say there are many titles of him. I just say that he is, as far as I know, father or grandfather of Jerry's famous solver and basilisk. So as I understand, solver JS is for incompressible fluid with the very nice tracking of phase surface, and basilisk is extension of JS. Stefan, please correct me if I'm wrong. For a compressible fluid, so it's
yes, mostly yes, mostly yes, but you can also do incompressible with basilisk.
Yeah, with basilisk. So that is the one of achievements. Okay, not one, but it's actually great achievements where Stefan heavily contributed. Again, as far as I know. So, Stefan, if I'm wrong, then please correct me. And the title, hello, Javier.
Hello, how's it going?
Of basilisk and Stephane Poppinet.
Yeah. But I said father or grandfather. So this could be better. So it's about dynamic contact lines with volume of fluid method. It's very interesting, at least for us, topic, because one of my students is doing that, but theoretically, not numerically. So we start seminar. I ask all our participants to mute their microphones, at least microphones. You can keep your video. Stefan asked us, or some of participants who can do this, to show face and to to indicate how it's clear or not. Yes, I can see how it's how his presentation is going. So yeah, indeed it's helpful. But if if the quality of seminar or quality of connection would go bad, then we should switch off our video as well. So yeah, then I switch off my my microphone, and Stefan, the floor is yours.
Okay, thank you very much. It is a pleasure to hear you say Zaleski in the Russian way, because I have a lot of connections now with Russian scientists, and also my father for a while, for a few months, was a citizen of the Soviet Union. So so was my intellectual father, Yves Pomo. He was not a citizen, but he stayed a long time in Novosibirsk. So I'm really fascinated by the work of the Russians. You said I was the grandfather of basilisk, but actually the real father is here, Stephane Poppinet, and he developed some codes with Ruben Scarnarelli and me, but there are other codes that I was more directly involved with Greta Tryggvason and Alexandre Guion. So this talk will be about the code development. It will be about hydrodynamic assist or coating, on which I collaborated with Yash and Thomas Fullana. I should even say I collaborated on it with Yuli, since I had long conversation with Yuli about it. Shahriar Afkhami, Alexandre Guion, Jacop, Buongiorno, Youssef Saadeh collaborated with me on the microlayer and on boiling, and Xian Bin Shen, Mandip Sani, and Daniel Fuster collaborating on microlayer, cavitation, and boiling. And there is this long list of Swedish people on which I collaborated on the parallel plate numerical experiment. So I first got interested in the contact line because my intellectual father, Yves Pommeau, had very passionate opinions about it, and he also had hot debates with Pierre-Gilles de Gennes and Stephen Hawking, with Hawking about it, and that got me interested. But then the real, maybe starting point was when Yuli visited our lab for 6 months, and he told me, you have to help me solve this problem numerically. So that was, I think, around 2000, 2001, 2004. And Yuli, correct me if I'm wrong. And so he got me interested in that problem and said, he used flattery, of course. He said, you have the best numerical methods. Only you can help me solve that problem. It turns out I didn't help him solve that problem. He turned to other people. But it still got me interested. And so what is the problem we're talking about? It's a problem of a triple point between two immiscible fluids and a solid. The solid is undeformable and rigid. And the singularity arises because there is a contradiction between the no-slip condition on the substrate, on the solid, and the fact that the contact line moves. Dissipation and friction diverge logarithmically. So to show that, you start from the equilibrium angle, the Young relation. Given by this Young relation, you can obtain it energetically or mechanically. And look at what happens. Well, you have usually you have advancing and receding contact angles in most of the experiments. And so if you believe the experiments and your eyes, you see that it is moving. However, I should note at this point that what you see is not the smallest things that can happen here. What you see is above a micron on the optical length. And we're going to talk about apparent contact angle, the contact angle that you see. So assuming there is this apparent contact angle is not curved, contrary to what I just said, just to make things simpler and find a paradox, you can integrate the dissipation integral epsilon here, and you find the dissipation is like log of A over beta, where beta is a slip length, sometimes also called lambda, and A is an outer length scale. So the first time I heard this argument from Yves Pommeau, there was Benjamin Levitch in the room, and he said, this is nonsense. You cannot have this logarithmic divergence. This is nonsense. So we already had a hint that continuum mechanisms don't like singularities. So what is to be done? Lawrence Scriven also noticed this singularity, and he said, well, this is really bad. Even Hercules couldn't sink a solid, because if you're sinking a solid, you have to plunge into the water, there is a contact line, and it resists the entry of the solid. So this is really a bad problem, as many people noticed. But more than to say this is a bad problem, I would like to express this problem a bit more precisely. And it's a bit like when you say there is a horrible problem, there is the turbulence problem, it's a horrible problem. But when you say that, you haven't said what the problem is really. So I think there are three problems that are of great interest, at least they are the problems of interest to me. What is a good mathematical model of the moving contact line? And you have to define good, and either it matches the experiments, or it has some mathematical qualities, or it has some qualities from the point of view of thermodynamics or the continuum mechanics. Second, given you have a good model, how can it be computed, assuming you have infinite computer power? Well, you'll soon see why we need infinite computer power. And third, if we have any model, we're given some model, can we make computations with finite computer power? That's an important question, of course, in practice. And since I mostly talk about simulations, that's maybe the question that interests me most. But of course, it's also the questions where we had made the smallest progress. And in fact, not even the first problem is, in my opinion, solved. And I will try to explain why. So you can subdivide the problem in other ways. You can try to solve the problem in equilibrium. There's no motion, just a steady contact line. You can try to solve the problem of steady motion. And finally, you can solve the problem of unsteady motion. And finally, I have a sub-problem, which will appear, but I will not dwell on it too much. Is the model local near the contact line? This is a very difficult question because it's not clear what local means here. So I will have to elaborate further on that. So to start with the first question, what is a good mathematical model? I will start with a proposal made by many people, which is the Navier boundary condition or Navier slip model. And so this has some advantages with respect to the singularity, you will see in a moment. And it postulates that the velocity profile penetrates the solid by length lambda. That is, there is some slip, there is non-zero velocity on the solid. And the relation is this du dy is u over lambda, where lambda is some material property. So there have been measurements of this lambda. It goes from undetectable, probably less than a nanometer, to 10 microns. We also did with the Swedish collaboration molecular dynamics, and there the slip length is less than a nanometer. So we can at least believe the slip length, if it exists, is small. Then, starting in 2015 with Shahriar Afkhami, we used the volume of fluid method. And to solve, so let's try to use this method to solve the tentative good model numerically, the good model of the Navier boundary condition or slip length. So how does the volume of fluid method work? It reconstructs the interface in each cell as a small discontinuous segment, and then it advex the interface by a space-centered velocity field. So if velocity field is like, you immediately see that when you do that, the velocity here is at a distance from the solid, which is here below. So you have an effective slip. That's one of the most important lessons you draw from this. You could also view this as an implicit evaporation if you are losing some mass, but this is not, in fact, implemented. This is what was done by Shahriar Afkhami. Actually, Shahriar, in his thesis, solved the static contact line problem. So in step one, he extrapolates the segment using the equilibrium angle or a numerical angle called theta delta. So in step two, so the extrapolation is done here. You see, this is the construction you had without the solid, and that's the construction inside the solid. In step two, you compute heights or widths. In fact, Sasha, you were kind to mention Jerris and Basilisk. Basilisk only has the widths method, not the height. So Basilisk will not work well for small angles. But in fact, even Jerris does not work well for small angles, because in these regions here, in these little regions under the interface between the solid and the interface, you totally don't resolve the fluid mechanics. So you cannot really do this, and it's a little better here. So moreover, this only involves VoF and implicit slip, as I mentioned in Jerris, but a real actual slip was implemented by Thomas Fullana in Basilisk. So Basilisk is an octree volume of fluid code developed by Stephane Zaleski. And this is how Thomas Fullana implemented the slip lambda by basically putting ghost velocity field in the ghost layer in the solid that are extrapolated using the Navier slip condition. So I mentioned several times that Basilisk and Jerris are octree. So this is what an octree is. It is possible that the idea of the octree was given to Stephane Zaleski by another Russian called Sergei Semushin, but we have no proof of that. And actually, I'm looking for Sergei Semushin, what happened to him. The octree, or the fully threaded tree, was published by another Russian called Koklov. But Then Stephane Zaleski made a wonderful tool out of it, and in particular it parallelizes, so the colors indicate the processor. So you have a, and this parallelization is only available in Basilisk. So Sasha, this is one of the very big differences between Basilisk and Jeris, is that in Basilisk you can do the contact line in parallel. So the parallelization is much better in Basilisk. So this is a curtain coating simulation. I've not defined curtain coating yet. I've not introduced curtain coating yet, but I will do that. We get to a grid size of 150 nanometers here. So this is good, but it's not the world record. So here we have the curtain coating setup. So you have this liquid that falls from the top with a dye thickness dc, falling velocity v. The falling height is hc, and it's untrained by this bottom plate at the velocity u, which can be very, very high, up to 100 meters per second, which looks crazy, but it has been done by T.D. Blake and collaborators. And if you zoom here, you see this important feature here, an inflection point, and theta m, the microscopic angle, the angle at the smallest length scale that we can observe or attain or measure or simulate. And here are some views of this process. This is a somewhat similar process of a plunging plate. I will come back to the plunging plate. Here is the experiment of Blake, Bracke, and Yuli. And so you see that this foot, it's reversed compared to my previous pictures. So the speeds are smaller actually than the ones that are sometimes measured of 100 meters per second. And now here's the photograph, the first photograph of this talk, or the second one, the third one. So this setup was used by Yuli and others to argue that it's impossible to have a local mobility law of this form where the angle theta m is a function of the velocity of the plate u. It is, of course, here when I say function, it's dimensional, and it would also, of course, depend on the material properties of the fluids, maybe on the roughness, maybe on other properties. But the idea, there is no local law of that kind. And the numerical proof of this fact by Yuli relies on using finite elements and trying to predict the apparent contact angle, the angle here at the inflection point, from various values of, it's missing here, the microscopic angle and the velocity, and showing that no agreement is obtained. So in this case, the angle at the small scale theta m is matched in this region to the experiment, and it's supposed to depend only on u, and then you continue a series of simulations or experiments at various velocities v here, but without changing u. So if a local condition exists, the experimental points here should be on top of the numerical points, which they are not. So an important point is the model is a free surface, and the capillary number is 0.273. But I have some doubts. I think the capillary number is higher in this case, but I will ask Yuli and he will tell me. Here is a close-up of the simulation by Yuli and Wilson and many others. And so this is a scale of 20 nanometers. So you see the smallest elements are much smaller than in our simulations. And they are finite elements using this triangular shape. New simulations were done 10 years later by the group of Satish Kumar, by Liu, Vander, and Carvalho and Kumar. And in this case, we have the same range of capillary numbers as in the Blake experiment. And you see, again, a curve showing the apparent angle. One thing that is seen here is you have these various colors, and the various colors correspond to various viscosity ratio. So the physical viscosity ratio is here. Why this is a 10 to the 4 viscosity ratio, which is unphysical, and this is the free surface viscosity ratio. So there is a strong dependence on the viscosity ratio. So there is a question, is the simulation by Wilson and others, is it affected by the viscosity ratio? Now, if you look at the capillary number that is announced in the paper by Wilson and others is 0.273. It falls here where in fact, the viscosity ratio does not matter. So in that case, it doesn't matter, but since as I told you, I suspect the capillary number is higher, near the critical point where you cannot have coating anymore. So the critical point here is at the maximum velocity, and I think we are a little bit higher in the Wilson calculation, but I leave that for later. So let's do our thing. So we redo all that with Basilisk, and first we are going to try to reproduce Liu, Vaundry, Carvalho, and Kumar from 2016. And Liu and others use a reduced system compared to the Blake system. So it's reduced in the sense that the height here is smaller. It's 1 centimeter instead of 3. And it's also reduced in the sense that the slip lengths that we're going to use are relatively large, of 10 microns. They are large compared to the nanometer slip length that I mentioned before. And we look for the stability window, which is between 0.1 Ca and 2.6. The Reynolds number and the Bond numbers also vary, but we will discuss the Reynolds number later, and we will not discuss the Bond number at all because there is not enough time. And we don't know much about its effect also. So and these are the simulation by Thomas. And so you see the falling curtain here, and you see the octree grid. And if you zoom in this region here near the foot, you see this thin air film. And there's a difference with the Liu simulations that we fully simulate the air film. We grid inside the air film. Liu and others, we're using a thin film model for the air film. If you zoom more, you see the thin film and the grid. And if you zoom even more, you see this the neighborhood of the contact line here. The contact line is 90 degrees. It doesn't appear like that because the curvature is extremely high here. The curvature is of the order of the slip length. So if we look at, and even sometimes much more than the slip length, as I will show. So, but the good news is that it converges at second order. The error in the contact line position converges at second order, and the error in the inflection point position converges maybe a little less than the second order. So it is, we have a way of converging a simulation, of having an adequate numerical simulation for this slip length model. So at least the slip length model is good for that. We have good agreement with the finite element simulations by Liu and others. You have good agreement for the critical capillary number here, which separates the steady regime for the regime where there is no steady solution, where that's the regime where you generate some kind of bubbles. I've shown the bubbles here. So what you call here sawtooth meniscus, the little white points you see are bubbles that form when air is entrained at towards the left here, and basically the static, the steady solution is not observed anymore. The contact line starts being unsteady in the laboratory frame. It's of course moving with respect to the solid, but you have an instability that creates these air bubbles here. And so I go back to this, so we get perfect agreement with Liu, with our method. We can also try to compare the apparent angles the angles at the inflection point. And so to the left is the result of Liu, I already shown you with the free surface, etc. And to the right is the result with Basilisk obtained by Yash Kulkarni. And Yash did something more. He also varied the Reynolds number. And you see there is it's not only an effect of the apparent angle, but there is also a large effect of the Reynolds number. The Reynolds number is varied by leaving everything constant, but just varying U and sigma. So you keep the capillary number also constant, and you can vary the Reynolds number. So this is very important because a lot of the theories are based on Stokes flow, and here suddenly you see that it's not Stokes flow at all. And this is a view of the different configuration. You have at low capillary number, you have the heel formation and large Reynolds. So you have a strong inertia that makes the thing sort of begin to splash. At the smaller Reynolds number, you're here. And when you are at the critical point, you're like this. We decided, in fact, Thomas decided to also compare with the Blake experiment, so higher HC, and that yields a more difficult comparison. Liu and others also tried to compare to the Blake experiment, and we are in agreement roughly with Blake, but we are not with Liu, sorry, with the other numerical people, but we are not so much in agreement with the experiment. And well, it's not known why. Maybe because of the slip length is not resolved, but I'm not convinced it's the slip length. This is something that remains to be investigated. Other experiments that exist are those of Marston and others. These were experiments where the best estimate of the slip length is 400 nanometers. So these were nicely resolved and nicely match the experiment. Well, there is maybe 10% error here, but the very nice match here is with the other numerics again. But the discrepancy is not as large as with the Blake experiment. Another interesting result that we obtained with this volume of fluid simulation is the confirmation that the curvature has a singularity. If you look at this is a zoom on the neighborhood of the contact line. The red point is the red line is the interface. Lambda is the slip length. We really are on this small scale here. And if you plot the curvature with a logarithmic scale in R, you see that the curvature is diverging logarithmically. And this is not a surprise. You can obtain it from thin liquid film theory. You can also obtain it from an analytical solution of Hawking for non-thin wedges indirectly. So this was known, but it's nice to see this happen numerically, and it gives you an indication of why you need so many grid points near the contact line, why we need 64 grid points per slip length. Another view of that is that was developed quite a lot by Jens Eggers, is to concentrate on a plunging plate experiment. In the plunging plate, you again have an advancing contact line with an inflection point, it can be argued that the situation near this contact line should be very similar to the one we had previously in the curtain coating. So it's just simpler. So Benny and Timpson predicted a scaling law where the thickness of the film H is like x to the power q, where x is the vertical distance here. If you are way above the inflection point, and it's predicted from Stokes flow theory. Well, we cannot verify that very well because our Reynolds number is of order 1, but you could notice that this this translates into the angle being like r to the m with all the distance, and m will be being this exponent q minus 1 for small angles. And so we can try to compare that, and we see here that we have and the inflection point is here where the variation of theta with r cancels. At the minimum of theta is the inflection point. So to the left we have the neighborhood of the contact line, and to the right we go to the large scales. And so the angle starts increasing again as we go where the Benny-Timpson theory should be valid. And we see that as the capillary number is increased, as you approach the critical capillary number, you approach the exponent m of 1/2, which is a theoretical angle. So maybe there is something there. Maybe with a little more efforts, we should be able to capture the Benny and Timpson theory. So that's the maximum we could do for the curtain coating. This is still work in progress. We still have to compare it to Blake and Yulee, but it's not over, but it's all I can tell you for the moment. So I'm sorry, Yulee, and even almost 20 years since you visited the lab, I still have not solved your problem, but maybe in the future. One thing we did, which was easier, was the withdrawing plate experiment. Why is withdrawing plate easier? Well, there is a clear separation of scale between the inflection point and the macroscopic length scale. The inflection point is located at capillary number to the 1/3 times LC, where LC I didn't write here, but LC is the capillary length obtained from gravity and the surface tension. The contact line is receding. The wetting occurs at a small critical capillary number when apparent contact angle vanishes, and is a range where Cox-Voinov theory applies. So what is Cox-Voinov theory? I will explain that later, but first let me show you the simulation results. So it's that was done using Jerry's. So it was very expensive because we couldn't parallelize. For large CA, there is a Lando, Levitch, and Derek in film. For small CA, there is not. So this is the case at small CA. So we run simulation, and for each static angle theta and for each grid size, we determine a critical CA. So this is one example. We measure the height of the contact line point. If it goes to infinity, like here, we are above the transition. If it's steady, we're below the transition, and this red line is, well, okay, maybe where the transition is. And so we plot all the critical capillary numbers with the grid size, and we found one of the things which really plagues simulations of the contact line with the usual methods is that the result depends on the grid size. So I will say later a little bit how to fix that, but a very easy, cheap fix, as even an easy cheat, is to say that there is a kind of effective slip length. If you have an effective slip length, then you can predict the critical capillary number, and you get this kind of prediction where phi is a parameter that enters the Cox-Voinov theory, and it's predicted. It matches the prediction by Jens Eggers for the thin film. So what is this Cox theory that allows us to find these nice things? The Cox theory says that g of theta is where g is some function I will explain, is the G of the equilibrium angle plus capillary numbers times log R against the distance to the contact line over Li. It's valid for small capillary number, and so it's only valid for this withdrawing plate experiment, not for the plunging plate of the curtain coating, because we don't have small CA in the other experiments. And it's valid in a range which for where R is much larger than the microscopic length and much smaller than L. What is the G function for a free surface? This is the G function, and it was obtained by Hugh and Scriven, I think, and then used by Cox for his theory. The Cox theory can be revisited because there is no reason to put the equilibrium angle here. If you have some microscopic effects at some scale Li, then you can put a theta d here, which is dependent on Ca. This is so. This, in my opinion, expresses better what happens in the range Li much more than R, much more than L. And Li summarizes all the effects of the microscopic physics: the slip length, the interface thickness, the diffusion length, intermolecular forces, dynamic effects on the contact line, etc., and other microscopic physics. And that's why I do not write it lambda. So these are the results of the simulations by Shahriar Afkhami. Here I plot g theta minus g theta of R. Here I plot Ca log R. And if the Cox theory is valid, we should have a straight line with slope 1. And instead we have these points. So we try to understand why we have this discrepancy. And our best results and best thoughts are that, in fact, you have a curved profile here because of the neighborhood of the microscopic physics here to the left, and here you have another curved profile because of the large length scale, which gives you eventually a constant angle. So this relaxes the constant angle. So it's only in between. So this is not perfect because you don't have a wide enough asymptotic range. And you need to have a wide range in log. So this is a very difficult thing to have a very large log of the scale ratio. And you need, of course, to have a very small CA, but that is achieved. So this is the best we could do on the withdrawing plate. So the withdrawing plate was is a receding contact line, then the plunging plate is an advancing contact line. So let's now do the final experiment where we have both an advancing and a receding contact line. Then we are even rich, we have 2 advancing and 2 receding contact lines. So the experiment is actually shown first here. So we use a variety of capillary numbers. CA005 is only the smallest one, and the one we used in the first paper. There is now another paper submitted with other authors in 2022 that you can find on the web. We use 3 methods to study this flow: molecular dynamics, phase field, and volume of fluid. The molecular dynamics here serve as a kind of replacement to the experiment, okay? And, well, you could say that molecular dynamics encompasses a lot of the microscopic physics that we want to have, not all of them, of course, but a lot, so it should help us advance all these issues. The system exhibits 4 contact lines to advancing. I already said that. We use a localized Navier boundary condition, a localized slip length with a constant contact angle. The contact angle was extracted from the MD simulations. And so we have a very tenuous gas phase, very small density gas phase. And the gas is water vapor, of course. There's only one species of molecules. The viscosity and the surface tension are usual. The system is very small, 50 nanometers, because we cannot do MD if the system is larger. The small size of the system, of course, is going to cost us in terms of asymptotic theory. And the plates are moving, the parallel plates are moving to the right and to the left. This system was already done by people, including by Blake, with molecular dynamics, but the difference here is that we have realistic molecular dynamics. Lots of people before Berg, Hess, and Peter Johanssen did this with Lennard-Jones potentials. But the Lennard-Jones potentials are not good for that because they have relatively large slip. Here, with these realistic models of the SiO2 molecule and the water molecule, you have hydrogen bonding between the substrate and the water, which results in very, very small slip. So we compare molecular dynamics to VoF. Here I say using Perry simulator. So this is the code I am the father of, unlike Basilisk and Jerry's. In fact, we used Basilisk in the 2020 paper with Thomas Fullana and Perry simulator in the 2022 paper with Johann Sundin. So to explain what we did here, I need to describe the diffuse interface method and also to discuss some issues with the contact line and volume of fluid. So here is a point of view of Yves Pommeau. As I said in the introduction, he is my intellectual father. And one should reconsider the van der Waals approach of Pierre Seppercher. Pierre Seppercher was a member of our laboratory when it was called the Laboratory for Theoretical Mechanics, which was a very nice name. And now it's called Institut Jean Le Rond d'Alembert. It's not my fault. And so when we were theoretical mechanics, there was a guy called Pierre Seppercher who worked with us, and he wrote this paper. That was the good old times when there was only one author per paper. And he did this. He obtained the contact line with this variable density field. Okay, so you have water here on the left and water vapor on the right. And how did he do that? Well, he used the phase field method where you assume that the density varies smoothly instead of the method we discussed until now where the interface is sharp. And he starts with a simpler free energy model than, if you want, I mean, with Gustav Amberg, we start with a simpler free energy, the Jackman-Amberg model, where this free energy is this double well function. I recall this expression for the interfacial energy, which is due to van der Waals. You can see it in his paper, which is, by the way, very nice. Kahn and Hilliard re-express it in terms of the other parameter C. I will explain what the other parameter C is later on. And so you add a bulk free energy, the free energy from the double well, to this interfacial free energy, which is a gradient squared. And the other parameter is used to compute the density rho and the viscosity mu. So the rho is rho 1 or rho 2, depending on whether you're in the water or the water vapor. And you consider the flow to be incompressible, which is an approximation, of course, in the water vapor, but it should be okay because the Mach numbers are terribly small. You get the Navier-Stokes equation here with this additional term, which is the surface tension term. Phi is the chemical potential, C is the other parameter. The other parameter obeys this equation, which has a diffusion term, which is in fact the divergence of the flux computed by a kind of Fick law from the chemical potential. And the chemical potential phi is given by this derivative of the free energy plus a Laplacian term. Kappa is the mobility of the model, and the free energy is, as I said before. And you need to supplement this model with boundary conditions. So I show you the model again. This is very complex model, so it may be a bit confusing at first, but the main point is that it has this order parameter C, which varies smoothly. The boundary conditions are no slip in that case, so that's to show you we can do that without the slip model. And the contact line moves because of evaporation through this boundary condition that controls the motion of the contact line. So it's an equation with a time derivative of the order parameters, which is valid only on the surface. The right-hand side here I will explain a bit later. It's related to the Young relation, to the relation that gives you the surface energies of all the interfaces. G is the surface energy density on the solid. So it has two values for the vapor and the liquid. The Young Laplace relation is given by this. Gamma 1, gamma 0, and gamma are the rescaled surface tension. So the gamma 1 minus gamma 0. This is gamma cosine theta E, so you have the equilibrium angle here. And mu F is called the contact line friction. That's the amount of energy you dissipate when you move the contact line at some velocity. The chemical potential C may seem a bit mystical, but one way to explain the diffusion by chemical potential is to perturb the bulk state by a small perturbation C, and then you find a usual Fickian diffusion equation. So the system has usual diffusion almost everywhere. And if you look at the solution then obtained by the phase field, you see these little arrows here, and you see the liquid in red here being sheared. And if I zoom, I will see near these little arrows, I see these white arrows going to the left. This means that, in fact, there is some matter that goes from the liquid region through the interface to the gas region, although we're in steady state. So that means that the interface is not moving with the fluid velocity, but the interface is, in fact, crossing by an evaporative flux. So you evaporate here, and then you recondense here. So, in fact, because you conserve volume in the incompressible formulation, you recondense fluid here. So you evaporate here, and you slowly recondense everywhere else. So here is the result, and you have interface angle, phase field, and volume of fluid all together on the same graph. So it matches somehow, but it's not perfect. Why is it not perfect? Well, for example, you can see here near this is on the right here you have the advancing angle, on the left you have the receding angle. Near the advancing angle, we don't match the final few nanometers when you approach the solid. The slope is not the right one. The inflection point is not at the correct angle. And then the models try to recover very quickly the static angle here, but the static angle is not observed in the MD. So the phase field by construction tries to match the static angle. This dotted line here, theta 0 is the static angle, and pi minus theta 0 is also the static angle, but on the other wall. And so it is good, but it's not perfect. Among other, the phase field is difficult to fix, but the volume of fluid should be fixed by other laws near the contact line. Sasha, how much more time do I have? Is it 45 minutes typically, or longer, or 1 hour?
You can use even 10 minutes more, but okay. Then we have less time for questions.
Okay,
so it's balance up to you.
So I was a little bothered because the molecular dynamic system is compressible and the phase field is incompressible. So I thought it would be more realistic to use a single species. I'm not sure it brings a lot, but we try it. So this is a model that I developed with Balu Najiga more than 20 years ago. And we recoded it in Basilisk. Basilisk is very nice to code things. I had made a bet with Sanjoy Banerjee that I could code it in 3 months in Basilisk, and I coded only 1D, but then the 2D was done by someone else called Alexandre Guion. And here you have the contact line with sound waves. And finally, it reaches equilibrium. We have not done the sheared droplet yet with that, but we're going to make it soon. Okay, and that was just an aside on how you could do other phase field models closer to the original Sepperscher and Van der Waals models. There are other things we learned from phase field models than just how to do simulations. We also learned something about the boundary condition, and this was noticed by T.Z. Qian, who is the father of the so-called generalized Navier boundary condition. T.Z. Qian actually disagreed with Gustav Amberg. Amberg had U equals 0 in the solid and a relaxation condition for C. Qian combines the two conditions. He shows that thermodynamically, you are allowed to combine them by combining this equal to 0 is the Navier slip, combine it with this relaxation term, and keep the relaxation term for the boundary condition for C. So now we have a boundary condition for the momentum and a boundary condition for the phase, and with both the same relaxation term L of C. You can understand L of C by seeing that these models have a Tench static solution, a Tench elementary solution. And if you substitute this elementary solution in this relaxation term L of C, you basically get the Young relation. So, so L of C becomes cosine theta minus cosine theta ek. So the new condition is a combination of the Navier boundary condition and the surface energy, and it's called the GNBC. And the other condition of Qian is identical to the condition of Amberg. So the GNBC, if you expand it near the Tench solution, looks like this. And where this is as before, this is, as I said, cosine theta minus cosine theta ek. That's the unbalanced Young stress. That's the amount of energy that is gained by moving the contact line from thermodynamics. And F epsilon is approximately that near equilibrium. Is this? It's a kind of smooth delta function. So now the nice thing about this is it kills the singularity we had of the divergence of the curvature. At least we think so, and it makes the motion less paradoxical. There is a paradox developed by Mattis Fricke and Dieter Botha that is removed by this GNBC. Indeed, what is the paradox of Fricke and Botha? Well, dyu is in fact d theta dt from usual fluid kinematics. So d theta dt is the variation of the contact angle, provided that dyu is continuous, that is, which it is not in general. And this would imply in steady state something like this. If you if you get a positive u if you use the GNBC, so it sort of removes the paradox of Fricke, which is obtained when you don't have this right-hand side term, and this is also 0, then you get u equals 0. I'm sorry, this is a little bit too short a description of the Fricke paradox, but just let it be known that if you use ordinary Navier boundary condition, everything is smooth, then u equals 0 and the contact line does not move, while with the GNBC, the contact line moves with the Young stress. The GNBC is used in large-scale simulations, in simulations at the human scale, not the nanometer scale, say of the millimeter or centimeter. And it's used in the following form. You replace the F epsilon by the real delta function. And you do finite elements, front tracking, finite volumes, etc. That was done first by Gerbeau and Lierre, and then by others. But this has a fake convergence. Because in fact, using a delta function here will introduce an error in theta minus theta ek. So I'm very upset by this. This is not a correct way of regularizing the. It's just a way of being able to do a numerical simulation. This is not at all a physically correct way of doing the contact line. And moreover, it has the defect that it's dependent also on the grid size. I mentioned earlier that lots of things are depending on the grid size and also this. So could we use the GNBC instead of a delta function with a smooth f epsilon? Well, pros that, again, as I said, removes the logarithmic singularity. And con, it is like mimicking the phase field on small scales. So why not use the phase field instead of that if that's what one wants to do? Maybe because it's complicated to couple a phase field on a small scale with VoF on a large scale, but otherwise it's not clear why it would be useful. I have given 3 problems. I said for a given model, can we make computations finite computer power? There was a suggestion we did with Shahriar Afkhami in 2009, which is to use as contact angle in the numerics, the contact angle in the microscopic with a logarithmic correction of the Cox form. Or another idea is to have subgrid evaporation. The problem with this method is that the range of validity of Cox is large. Only in some cases you need small capillary number and the large scale of the system much larger than the molecular scale, which is not the case in this molecular dynamic system. It's also not the case because of Reynolds number effect that eat the range of validity of Cox or other or Bennett-Simpson or other asymptotic methods. So this is the end. We don't really know what to do to extend the range of validity of the numerics to larger grid sizes. And I'm ready for questions.
Thank you very much. Thank you. Yeah, so
going to reformat the slides so I can see your faces when you ask questions. I see that Yuli is upside down.
No, that's because of your talk. It put me upside down. So
sure.
I have about a dozen questions and 100 comments, but let me just put one. The whole talk is in the paradigm that there is the contact angle and the contact line speed. They are linked. One is a function of the other, right?
No, there's not this paradigm. I mean, I'm trying. It is a hypothesis that I'm trying to prove or disprove, as you did.
Yes. I will set my views aside. So, and all this revolves around interpreting a single curve experiments, be it by Blake, be it by somebody else. But there is an experimental paper published in 2016 by Karim, Steve Davis, and Kavehpour, Steve Davis and his group, published in Langmuir, where they've shown that for the same substrate, and we have the same substrate and the same contact line speed, but the spreading could be forced, like plunging tape, or spontaneous, like spreading drop. And they've shown that the angles are different for the same speed and the same substrate and the same fluid. Different well beyond the experimental error. Therefore, the whole point of making the angle a function of speed or vice versa is disproved by experiments alone without any theory.
Mm-hmm.
Therefore, after that, in a sense, they go beyond Blake. Blake's curve needs interpretation. Their curves do not.
Okay.
And the question I was about to ask.
I thank you for this reference. Maybe we will switch and try to explain their experiment instead of Blake now.
Absolutely. But in any case, the angles are markedly different. And I mentioned this paper in my review in 2020. Therefore, it is there, the reference, I mean.
Okay. I have your review. Yes, I have your review.
Yes, and in that it is mentioned that paper they propose a rule of thumb: use this theory for this, use that theory for that. But the point is, regardless of any theory, the experiments show that the contact angles for the same velocity are different depending on the flow.
Mm-hmm.
And the question I was about to ask, at the very beginning, you spoke about the removal of the singularity, but in your code, in the actual code, what angle do you put in?
Well, good question. We put a fixed angle at the grid scale. That's
you put some fixed angle.
Some fixed angle, yes.
And then the question is, why do you use the inflection point as the measure of the apparent angle? Because the inflection point could be a centimeter away from the contact line.
Yes, in some cases it could be, but in the cases that we simulate, especially in the curtain coating, it's very close to the contact line.
In the curtain coating, Blake gives the accuracy as about 20-25 microns. But I spoke to him, and he said this is just, well, with a margin. In fact, it was smaller, the resolution.
Mm.
But even with therefore with Wilson, we used the largest possible resolution, so we're interpreting everything, and we varied the slip length all the way.
No, I know we did vary the slip length, yes. The
contact angle. Therefore, even then it was impossible to describe Blake's experiment. But now we have experiment by Karim, Davis, and Kavehpour, which supersedes Blake's experiment because they were just shown without any theory that there are different angles for the same contact line speed.
Yes, I agree, but there are other things to understand in the system than the dependence of the smallest angle, the angles at the smallest scale with the velocity. There are also issues such as the order of magnitude of the curvature, the existence of evaporation, the location of the inflection point, the feasibility of numerics. These are all questions which are independent of, in fact, what the microscopic angle depends on.
Quite the contrary. Once you put, these are all functions of what you put into the model, of what slip you put into the model, of what the surface tension, how it behaves, and of what angle you put. The rest will follow. It's not that they're independent.
Yes, I agree. But we, as I said at the beginning of my talk, we simplify. We start with a very, very simple slip model. There could be many other models, and all of what we do, we would have to restart again every time we use a different model. So if we used an interfacial formation theory, that's for those who don't know, that's a model suggested by Yuli, then we would have to code this and redo everything. And you know, there are many cases in which we would have to do essentially redo everything.
Yeah, well, yes, but why redoing? I would suggest you review experiments to see, well, if the model puts in as the input something which is markedly different from experiments, there is no point in investigating such a model. Because experiments, in a sense, they decide, well, they give us an a priori understanding of what is going on, and the model is actually, well, refining.
Yes, you are perfectly right. We should have better models, and these are only you know, the first attempt at modeling, at least in the framework of volume of fluids and the codes I collaborated on with my collaborators.
We have another question. So yeah, Matis?
Yes, Stephane, thank you very much for the talk. Can you hear me? Yes.
Yes, I hear you.
Okay. At least I would like to add the comment that in the section that you've shown on the generalized Navier boundary condition, at least there, the contact angle is not a priori a fixed function of the contact line speed, because there you have the kinematic factor, which takes into account the contact angle variation, I guess. So my question is, maybe it was a bit quick in the talk, so how did you make the transition from the diffuse interface context, where I think the GMBC is most naturally formulated, to the sharp interface? Is there any rationale for that?
What do you mean? What do you want to do from the diffuse interface to the sharp interface? Can you repeat the question?
Yeah, you had the equations formulated in the diffuse interface, like Guion originally did.
Yes, yes.
And then you kind of did the transition to the sharp interface, where you had that f epsilon of x function,
yes,
which some
yes. So that the Tench solution. Let me, if I can go to the front. Do you see my slides?
Yes.
Yes.
Yes. So you
not
have,
full screen. You can make full screens and it will be bigger.
F5.
So, yes, you use this Tench solution, and if you substitute this Tench solution into TZCAN, then you get that near the Tench solution, expanding the GN.
Stephane, but
does that answer your question, Mattis?
Yeah, so that's why you got that expression that's in the middle of that slide for the f epsilon of x. Okay, thanks.
Okay.
But in that theory, which I believe was originally proposed by Ren, where you have velocity proportional to the difference of cosines, if you look at the
by Ren, yes,
if you look at the theory itself, sort of examine it closely, you will see that the driving force for the contact line is friction. So
yes,
we are used to the situation when friction resists motion, but apparently in some parts of the world it's the other way around, and friction reduces motion.
It's not the friction resists motion. I disagree with you.
No. In their theory, it induces motion. Look at it, examine it, and you will see that that's what happens there.
Sorry, we are not.
That's why formula they have
infinite time.
Of the
sorry. Once we need to stop, and I'm as the organizer of this seminar, just to say that anything or nothing can be a final proof of a result. So there's some people saying that, and many people saying that experiments should final proof of everything. Actually, it's my experience shows it's not. It's very easy to do nice experiments, which looks nice, but it shows something very different, and it very depends on how we understand what's happening. So it heavily depends on the theory. This is my opinion. So I believe all means of theoretical, numerical, computational, which is to say, or experimental, should be used to solve the problem. So it's more or less kind of philosophical question. In particular, what I found today in the presentation, it's very close to my kind of recent interest. So it's using CFD to prove something, to investigate something, to go down, to go to the theory, and also analyzing the numerical results to find to refine the theory. So that is the I believe this is important part, and it's not right to say, yeah, you should do this one or you should do that one. Everything is important. Everything should find its own place. All our results should find all place in the whole picture. I'm talking this in particular because one of participants is still here is Professor Pukhnachov. He is my supervisor many years ago, and 22 years ago, 42 years ago, as I remember, he gave me a contract to do a topic which was presented today. It's very interesting, and I can compare what we did, and so it was it was 1980. It was part about the Navier-Stokes Navier boundary condition, and the only difference from my report that time, it was that you are using the viscous stress only. And I said, no, it's complete, not me, but what I revised, it was complete pressure. So it's both hydrostatic or hydrodynamic pressure plus viscous force. So that is the end. I remember you didn't mention, Stephane, Dusan. Is it right to pronounce? But that time in 80s, she was famous, and she published papers in Journal of Fluid Mechanics that time.
Yes,
and
I learned about this from Dusan. I learned about this from the review of Dusan and Davis. Yes.
Yeah, exactly. So that is it's kind of returning 40 years back in some sense. So I'm very much enjoy your presentation in many respects. Even I could not go to the bottom of all your results, but I see that this field is still progressing, and there are many challenges, and the discussion with Yuli or initiated by Yuli shows that there is many things to do, and not all of us, but the people who are specialists in this field have many things to do to explain, to convince us that this is the case, this is how it should be, and how it looks like. So if Stephane, if you have something, a few words to say at the end, and sorry, we should finish our seminar.
I should say that I'm available for discussions by email if anyone has questions about the seminar. And I can also send the slides of the seminar, whoever wants them.
Yeah.
And we would be happy to have further discussions with anyone here on this topic.
Yeah. Thank you very much. And we close. And thank you very much, Stephane, for inspiring presentation, and the presentations are some presentations with many new results, but also the presentation which open new questions and excite participants to work on it. And from that point of view, I believe this is very good. So this seminar was recorded. And now I stop recording, and using permission from Stephane, the video file will be uploaded to our YouTube, so all of you could look through all the slides again. In particular, I make a list of slides to look again. So I noticed that some participants also did notes during the seminar. So, and
Alex, how do we find on YouTube?
I'll send the reference, but if you go to the invitation I sent to all of you, or almost all of you, that at the end there is the list of next seminars, and it's written that all seminars are on that link on the YouTube, on the very bottom. If you go to the very bottom of
thanks.
Yeah. If not, if you couldn't find it, contact me, and I'll send that link. And as Stephane said, any particular questions about this topic, you can send by email to him for further discussions. Right. Okay. So then, thank you very much, and I'm close this seminar. So I'm yeah. So I stop recording.